Hello everyone, I hope we're all doing well and I hope you all had a happy Memorial Day. Today we're going to be talking about tangent lines, and our objective is that students will be able to use knowledge of tangent lines to solve for missing segments. So one application of tangent lines in the real world, we're actually going back to engineering like we do with a lot of circle things. Tangent lines are everywhere in design and engineering, including the same amusement park rides we discussed last week. For example, many Ferris wheels have support beams that are tangent to the circle that makes up the wheel itself. Alright, so you don't really know what tangent lines are yet, so you have some options. You can either pause the video here and write down one application of what you think a tangent line might be, or you can listen on to some more of the video until we find out what a tangent line is, and then come back and fill this box in. It's up to you, but make sure you put in one application that you can see in the real world for tangent lines into this box before you turn in your worksheet. All right, so hopefully you have an idea down. Let's move on and look at our notes. So this notes question says, consider the pictures below. And by that, we mean these three pictures here. Describe the difference between the three pictures using the words interior of the circle and exterior of the circle. So interior of the circle, this means inside. And exterior means outside. So in this box, I'd like you to just in a couple of sentences describe the differences between these three circles and the lines that are either outside or inside of them. All right, let's move on. So you definitely notice here that some of the lines are outside of the circle, some of the lines are touching the circle just a little bit, and some of the line goes inside the circle. So two of these have very specific names that we use very commonly, and we're about to get definitions for those names in just a moment, those vocabulary words. But let's identify them here so that we know what we're looking for. So this first picture that has a circle with a line that's going through it, and it intersects that circle twice. This is called a secant line. Now this line right here that intersects the circle just once, this is called a tangent line. And what we want to notice is that most of the lines that we draw that connect to a circle are going to be secant lines, right? Tangent lines are very special because if I were to move this line over just a little bit, then it would be a secant line because it would be intersecting twice. If I were to tilt this just a little tiny bit, then it would be a secant line because it would be intersecting twice. So in this way, tangent lines are very specific and very special because they touch the circle, but they only do so in one spot, which means they're entirely outside the circle and they only intersect once. All right, let's go through some formal definitions. So we've already talked about this a little bit, but a secant line is just a line that intersects a circle in two locations. And a tangent line is a line that intersects a circle only once. Now, something we want to keep in mind with tangent lines is some people would look at a picture like this and say, well, this line only intersects my circle once, so therefore this is a tangent line. That's not exactly true, because keep in mind here that we are talking about lines in both cases. We're not talking about line segments. So remember that lines go on forever. They extend forever. We know this from the very beginning of our geometry classes. And if we were to extend this line segment into a line that goes on forever, we would see that it would, in fact, intersect this circle a second time. So that's one of the reasons, like I mentioned earlier, that tangent lines are so special and specific because they only intersect in one place. They only touch it once. All right, let's move down to this fact that we have. So this is fact one. It's actually the only fact that we're going to go through today. If we worded this a little bit more specifically, we could call this a theorem. But this fact says radii and tangent lines are perpendicular. So the first thing we want to notice is that radii, that's just the plural of radius. So that remember that radius is any line segment going from the center of our circle to the outside of our circle. So every radius is the same because that's the definition of a circle. So in this first picture that they gave us, we have a radius, right? AP is a radius. And we also have this tangent line here, this line that goes like this. And their claim, this fact is saying that these form a right angle. Now you can look at that and say, yeah, it kind of looks like a right angle, right? And we could go through the proof that this is true. If we were in class right now, we would draw a circle with a compass, we would draw a radius, and we would draw a tangent line. And then we would measure the angle created by the radius and the tangent line. Now you guys might not have that option, especially if you don't have a protractor or a compass around, but what you can do is make sure that this is scaled correctly so your circle is actually a circle. And then if you grab a piece of paper or a book or anything that has a right angle and hold it up to your screen here, you should see that this is in fact a right angle. All right, so our first question here is asking us to identify two groups of points that would form right angles in the picture below. Now I used groups of points. That's not really a very technical term. Basically, I'm asking you to identify two right angles in this picture, but remember that we need 3 points to make an angle, right? So if I have an angle, it's something on the outside, my vertex, and then something on the other side to make my angle. So if we want to see which ones are right angles, we're looking for when a radius is intersecting with a tangent line. So the first thing we need to notice here is that CD appears to be a tangent line, because if I extended it, it would still only touch in that one place. And the same thing with CE. This appears to be a tangent line because if I extended it, it still only touches in that one place. So if I'm looking at those two tangent lines and I'm saying, oh, I know that if I take a radius and I intersect it with that tangent line, then I know I'll have a right angle. So one example of that is if I made segment AD, then this is a radius, AD is a radius, DC is a tangent segment, so therefore this is a right angle. So my first angle that I can identify is angle ADC. Now I could do the same thing on the other side, and I could say I know that AE is a radius because it's from the center of my circle at A to a point on the outside of my circle E. And I know that when I take a radius and I intersect it with a tangent segment, then I get a right angle. So that means that angle AEC is also a right angle. All right, so we're going to talk about a theorem that we're going to have to remember a little bit. And then we're going to refer back to that picture that we were looking at before and see if we can make any conclusions. So first we need to remember the hypotenuse leg theorem, which is from a while ago. This is from Module 2 when we were talking about congruence of triangles. So the hypotenuse leg theorem says, if two right triangles have a congruent leg and hypotenuse, then the triangles are congruent. This is great because it essentially means that if I do not know everything about my triangle, but I have a little bit of information, like if I know that this side and this side are congruent, and I know that my hypotenuse and my hypotenuse are congruent, then I can say that these two triangles are congruent, which is really useful for us. Now this next question, what can we conclude about A and B? That's referring back to the previous picture. So let's look at that picture and see what exactly is A and B. Okay, so A is this segment right here, so segment DC, and B is this segment here, segment CE. So they're saying there's something we can conclude about these two segments, segment DC and EC. And I think by looking at them, if I were to ask you in class, well, do you think that one of them's longer? Do you think that one of them's shorter? I'm pretty sure that you guys would say that they look to be about the same size. Well, is there any way that we can prove that? Why don't we cut this in half like this? Now, the reason I do this is because we have right angles, and it's always easier to work with right triangles than it is to work with a random quadrilateral of some sort, right? We know a lot about right triangles. We can use the Pythagorean theorem if we know we have a right triangle. We can use the hypotenuse-leg theorem if we know we have a right triangle. We're not going to need this right now, but if we were to need any of our trig functions, we could do that if we had right triangles as well. So right triangles just take a lot of our tools that we have and allow us to use those. So if we look at these two triangles here that I just made by cutting this quadrilateral in half, I first see that we have a shared side. Now this is something that you should remember from back when we were writing out proofs, right? We did a lot of shared sides, shared angles, right? And the shared side is the side AC. The reason we call this a shared side is because it's in both triangles, right? AC is part of triangle ACD, and AC is also part of triangle ACE. Now, if we have a shared side, which means that this side is in both the top triangle and the bottom triangle, that side's going to be the same length in both cases. So that means that this red line is telling us that the hypotenuse of both of these triangles is the same. Now I know that this is the hypotenuse because it's across from the right angle in both situations, right? So this is the hypotenuse. I know that these are both right triangles. I know they have the same hypotenuse. So if I wanted to use the hypotenuse-leg theorem and say that these two triangles are congruent, the only thing I need next is the leg, right? So if I look at the legs here, my first leg is leg DA, and the leg on my other triangle is leg EA. Well, what's special about DA and EA? We know that both DA and EA are radii of the circle, right? And we also know that all of the radii around the circle are the same length. So if I say that this radius is 5, for example, you know that this radius is also 5 because the radius everywhere is the same. Now what that means for us is that we have two equivalent legs. And that's really important because we already knew we had an equivalent hypotenuse. Now we have two equivalent legs. And we have right angles, so we know we're working with a right triangle. That means we can use the hypotenuse-leg theorem. And if these two triangles are the same, that means that the corresponding sides are also the same. So that means that A and B are also the same. So essentially, the conclusion we come to after doing all of this thinking is that A is equal to B. These two lengths are the same length. Now we just did a lot of talking, a lot of thinking. Why don't we write this all down? So I'm going to do a very informal proof. And the way I'm going to do that is I'm just going to outline what we need for the hypotenuse-leg theorem, right? First, we need to say, well, I have right angles. Then we need to say the hypotenuse is the same. Then I need to say the leg is the same. If I have these three things, then I know that the triangles are congruent. And then finally, I can say that A is equal to B. So these are my statements, right? These are the things that I'm claiming. I have right angles, my hypotenuse is the same, the leg is the same, therefore the triangles are congruent, and therefore the lengths A and B are the same. Now, what are my reasons for this? Well, first, I have right angles. I'm going to use a shorthand for because, which is B/C. This just means because. So we have right angles because the radii and tangent lines are intersecting. And we know that that's true. Again, this is just a really general proof, right? These are just our big ideas. We're not writing a very specific proof right now. All right, we said the hypotenuse is the same. Why did we say that? Well, we said this is the same because it's a shared side. Then we said the leg is the same, and that was because the legs are both radii. And we know that everywhere the radii are the same. And then we say the triangles are congruent because of the hypotenuse leg theorem. And then we say A is equal to B because corresponding parts of congruent triangles are congruent. If you remember from Module 2 again, when we were proving congruent triangles, we did a lot of this. Corresponding parts of congruent triangles are congruent. All right, let's take a look at number 1, which is the first time we're going to be diving into some numbers in this lesson. So number 1 says, in circle A, the radius is 9 millimeters, and side BC is 12 millimeters. Find AC. Well, this should be pretty easy, and the reason for that is because this triangle, we know, is a right triangle, because we know that AB is a radius, and we know that BC is a tangent line. So if this is a right triangle, and the radius is 9, and BC is 12, we just have to find AC. Now, there are several ways for us to do this. The first way is to use the Pythagorean theorem, and that's the way that I would suggest to all of us because I think it's the way that we're most familiar with. So let's label the side C. I'm going to label it C because it's the hypotenuse, because it's across from the right angle. So if I use the Pythagorean theorem, I'm using A squared plus B squared is equal to C squared. A and B are my two legs of my triangle, so that's 9 and 12. So I have 9 squared plus 12 squared is equal to C squared. 9 squared is 81, 12 squared is 144, and that's equal to C squared. At this point, you might want to put this in your calculator, or you can try to do it in your head. I believe that this comes out to 225. Now, we know that 225 is much too big. It doesn't make sense in this circumstance, and that reminds us that now we have to take the square root of both sides to get rid of the squared on the C. In the end, we should get that C is equal to 15. So that means that side AC is 15 millimeters. Now, the next question asks us to find the area of triangle ACD. So this is interesting because we're taking an area question, which is something we learned later on in class. And we're combining this with a construction question, which is what we started the year with, which is really interesting. All right, so looking at this triangle, we need to pick a base and a height. Remember that our base and our height always have to be at right angles. And if we have a right triangle, we can just use the two legs, A and B, as our base and our height. We also know that area is equal to 1/2 base times height. So that means area is equal to 1/2 the base, which I'm going to say is 12, and the height, which is 9. Half of 12 is 6. 6 times 9 is 54. So that means that the area of this is 54 millimeters squared. All right, let's move on to our final question, which says find the perimeter of quadrilateral ABCD. Now this requires us to remember and use the fact that we came up with in our last question. And that idea is that BC is the same length as DC. We also know that our radii are the same. So that means this is 9. So remember that when we ask for perimeter, we're asking for how much fence would it take if I were to build a fence the entire way around the outside of my shape. So you could do a lot of fancy calculations, and you could say like 2 times the side if you know that these two are equal or whatever. We're not going to do that. We're just going to march around our picture and see which sides we need to add together. So I'm going to start here at B, and I'm just going to go around. So this side is 9. If I keep going, this side is also 9. So I'm going to add another 9 there. If I keep going around, this side was 12. So I'm going to add on a 12. And if I keep going here, this side was also 12. So I'm going to add on an additional 12. Now if I add those all up together, 12 plus 12 is 24, plus 9 is 33, plus another 9 is 42. So that means that the perimeter of this is 42 millimeters. All right, you should be prepared to work on practice level 1 and practice level 2. Practice level 1 are a lot of questions like part A, where you're trying to find sides of right triangles that are formed from radii and tangent lines. Practice level 2 is a little tiny bit more extensive and has to do with all 3 of these types of questions. Good luck, and if you need help, remember that we have live coach class, or you can message any of your teachers. Have a wonderful day.